Okay, we've got a 60 horsepower, 220 volt DC shunt motor. Efficiency is 81%. Got a field resistance, shunt field resistance of 105 ohms, armature resistance of 0.075 ohms. Okay, at full load, determine total power input in watts, your line current, total copper losses, and your stray power losses. Okay, there's a few things that'll help you out here. They want power input in watts. They're going to ask you for line current. You'll use that later on. Okay, what do we know about the line current on the shunt motor? Okay, if we look at the line ladder there. Okay, the line current.
The armature current
Right.
plus the field current.
Armature current plus field current. IT is your I line, right? Okay? So if we're given, or we calculate our line current, we can then use that to subtract the field current, which we can calculate, and come up with the remainder being the armature current. Yeah.
I didn't get, can you explain that one more time?
Okay.
Sorry.
Remember, IT, coming from the power supply, is IA plus IF. Okay? So if we can calculate IF and subtract it from IT, that will give us IA. We're going to use that later on. Okay? Now, so the first thing we want to calculate is our total power. Total power input, watts, right? Okay. If we have power out, 60 horsepower times 746 watts per horsepower gives us a power out of 44,760 watts. That's our power out. Okay? We know our efficiency is 81%. So we then go and put the efficiency formula, rework that. Power in is power out over efficiency. Okay? 44,760 divided by 0.81. Okay, don't forget to change that percentage to a fractional number. Okay? Gives us a grand total of 55,259 watts into the motor. Okay? Questions so far on that? Pretty good with that? Okay. We're going to come over here, we got line current now. Line current should be very simple. Okay, power in divided by our line voltage, 55,259 divided by 220. Okay, you're going to give us a grand total there of 251.2 amps. Right?
Yeah.
Okay, we're going to need that later, so keep that. That's why they had you calculate line current. Okay? Now let's go down here to copper losses. Okay. Got our field current through our shunt field. 220 volts divided by 105 ohms. E over R, right? Gets you 2.095 amps. Field loss, again, I squared R. There's that I squared R for our field losses. Okay? 2.095 squared times 105 will give us 460.8 watts lost. Okay?
For the field current, is it the line voltage divided by the field resistance?
Yes.
It's always
Yes.
at that. Okay.
Right. Your line voltage, your applied voltage, the voltage that's on the field. In this case, it happens to be the same as the applied voltage. Okay? If it's a different configuration, okay, you're going to have to do the math to calculate what that is. Okay? So you've got 105 volts there. Okay? 105 ohms for the resistance divided into 220 volts gives you your 2.1 amps. Okay? Now your armature current. Here we go. Armature current is your line current minus your field current. That's why you had to calculate your line current. Okay? Armature current is your line current minus the field current. We come up with 249.1. Now we can use that to calculate the armature losses. Again, I squared R. 249.1 squared times 0.075 gets us 4,654.
Is it line current, the IT?
The line current is IT, correct. Okay? So you gotta be careful sometimes, you know, you're thinking of it one way, but it's referred to in another. You gotta make sure that you understand the total current is the same as your line current. Okay? Now, we're working with a DC shunt motor. Here we go. There's our total copper losses up there. PCU, P copper, power in the field plus power in the armature. These are both losses, right? Okay? 460.8 plus 4654 gets a total losses of 5,115, right?
Yes.
Okay. Now we're gonna come over here to our total losses there. Okay? Total power loss. We know our total power loss is P in minus P out, right? Put in so much power, we get out so much power. What didn't come out is what we lost. So P in, 55,259, minus our output power. Okay? This is our output power. Input power minus your output power will give you your total losses of 10,499. Okay? Subtract our copper losses, 5,115, gives us 5,384 stray losses.
Do all that to find the stray losses.
All that to find the stray losses. Yes. Okay? Questions?
Now, they're calculating this when they're setting up a system. When the system's running, are you having to go back and redo these calculations at some point? Like, trying to get an idea of how it's gonna be used in real world.
If you know what your losses are, your copper losses, you know what your stray losses are. If your motor, if the bearings start going out, your stray losses are gonna start going up, right? Okay? You're not gonna put your motor on a dynamometer and measure your power out. But all of this goes to the understanding of the motor. If you can understand the motor, where the losses are coming from, where all the various components of the power is being used, you can better troubleshoot and work with and understand the operation of a motor. Okay?
When you say troubleshoot,